All right, great. Thanks a lot for having us. So the title's changed a bit. It's a little bit of a homage to our discussant here who wrote a very influential paper with a related title a while back. So this is Characteristics or Covariances, a Unified Model of Risk and Return, and it's joint with my longtime co-author Seth Pruitt, who's here, and one of my students from Chicago booth, Yinan. All right, so this is not going to be a paper where we're innovating on the question. The question has been around for a really long time. Why do different assets earn different average returns? Right? And the conceptual answer to this question is clear. We all know it. You get different compensation for bearing different amounts of risk. But that conceptual answer runs into problems in the data, right? A reliable risk-based explanation of the differences in average returns that we see across assets is elusive, right? This is what we call anomalies. All right. Now, in terms of the history, we spent 40 years or so on an empirical search for an asset pricing model that captures risk and at the same time uses that risk exposure to understand the differences in compensation across assets. And all of that literature sort of focuses on linear factor models of this form. And that's where we're going to be talking about things today. But even with this fairly simple structure to think about risk in a cross-section of assets, we run into a lot of hard questions. All right, so the hard questions that we deal with are things like the factors are unobservable. Right? We don't always treat them that way, but the factors are unobservable, and that's going to be a big hurdle both sort of economically and in terms of the statistics of what you try to do. And then, of course, the loadings are unobservable as well. We sort of always deal with that, right? We'll concede that we don't see the loadings well, but we treat it as though we do see the factors. All right, so I'd like to break down what's been done in the literature into kind of two common approaches for dealing with the empirical obstacles that you face when you do cross-sectional asset pricing. The first I would call sort of the pre-specified factor approach. All right, and this is the most common one. This is the one we all know and love. It's the Fama-French approach. All right, so we're going to take some factors that we build ex ante. Our construction of those factors, it's going to be somewhat ad hoc. It's going to be based on some knowledge that we've accumulated over time about asset behaviors. All right? So in order to do this, you have to have some previous understanding of the cross-section. And then when these sort of models are actually implemented, on top of that, they're implemented in sort of an ad hoc way. So we'll do things like be a little bit schizophrenic about how we estimate the model. We'll write down a static beta model with Fama-French factors, but then we'll estimate it in a rolling wave, for example, to build a little bit of, absorption of time variation and risk exposures. All right. Now, there's something that's very nice about this approach as well. You want to use this conditioning information. You want to use the stuff that we've learned from the history of returns when we build our models. And the Fama-French or the pre-specified observable factor approach does this. On the other end of the spectrum, to deal with the fact that we don't observe factors, there's an older literature. Think about papers like Connor and Karachik. They wrote a sequence of these back in the 80s and 90s that treats the factors themselves as latent. All right? So essentially what they do is they use the panel of returns and they estimate latent factors. They acknowledge that the factors are latent and they estimate via PCA. All right? So I like this approach a lot, because it doesn't make this sort of Herculean assumption that we get to observe the factors, but it itself has some other limitations, right? So it's only going to accommodate static loadings. I think we know now that conditional models are really important for understanding asset prices, so that's going to be an important limitation for us. And it also has this limitation in contrast to sort of the Fama-French approach that it only relies on the information in returns themselves. We might have a lot of useful conditioning information available from other variables that PCA is just not suited to use. You can't bring it into that estimator. All right. Now, I think there's a strength, right? These are just two sides of the same coin. The strength is it doesn't require that previous knowledge. It doesn't require it to be sort of brought into the model in an ad hoc way. All right, so that's my little brief history of cross-sectional asset pricing. Let me tell you a little bit about what we do in this paper. We're going to introduce a new method for thinking about cross-sectional asset pricing, for understanding cross-sectional risk exposures, and for understanding the risk compensations that go along with that. The method is called instrumented principal components analysis, and there's a sort of econometric theory paper where we develop the properties of this separately. Okay, so it's same co-authors here. But I want you to take away the following sort of features of this new methodology that we're going to introduce. First of all, it's going to be a latent factor structure, so much like the type of PCA analysis that we saw 20, 30 years ago. But we're going to modify the model in a way that we can kind of conveniently handle time-varying loadings. All right? It's not that we haven't thought about time-varying loadings and latent factor models before. It's that we've sort of known that we have to use the Kalman filter, and that's a real pain in the ass. So we're going to have a solution that gets around that in a much more convenient estimator. All right? This estimator is going to basically have the same computational cost as PCA, which is effectively instantaneous. It's really cheap to compute. All right? So it's going to be similar, but it's going to have this really nice feature that it can handle conditional models. All right. Sort of offshoot of this is that automatically, once you start thinking about this type of structure, there are going to be these nice asset pricing tests that emerge very naturally. All right, so there are going to be asset pricing tests that exist in a well-specified model. It's not an ad hoc model. So now when you build asset pricing tests off of the model, it's really easy to understand the properties of these test statistics, and you're not going to run into a lot of the problems that you run into in the preceding literature. So one thing I'd like about being able to do asset pricing tests in a latent structure, a latent factor structure, is that you're not asking the typical Gibbon-Ross-Schenken question when you have observable factors x, y, z. They ask, do x, y, z explain the differences in expected returns across assets? I run regressions onto these observable factors, so that's like the assumption that goes into the model. I get to see the factors. Instead, you get to ask a more general question. You get to say, do there exist some set of factors that I'm going to allow myself to potentially estimate that explain the difference in average returns across assets? So I like to think of what we're doing here as generalizing the old-style Gibbons-Ross-Schenken test. So we'll go through that in more detail as I proceed. All right, so those are the methodological takeaways. This is primarily an empirical paper. So what I want you to take away from this paper on the empirical end is that we're going to estimate a lot of different models, various number of factors. You only need 2, 3, maybe 4 factors to describe the cross-section of returns well. All right, that's not so surprising. We have a lot of like 2, 3, 4, 5 factor models that exist out there. But what's kind of cool about the model that we come up with is that once you use this model, once you estimate the factors that are most consistent with the data instead of trying to pre-specify them, you find no alpha. And we're going to look across many, many characteristics. We're going to use a high-dimensional and expansive view of the type of characteristics that people use to predict returns and that people have argued have alpha. And we're going to show that things that look like they have alpha with respect to the Farmer-French factors or Luzang's factors, they just aren't going to show up as alpha in our estimation. So what I'll show you is that characteristics, this conditioning information I was alluding to on the previous slide, characteristics at the stock level, they are really informative for the behavior of asset prices, absolutely. And they are really informative for understanding differences in expected returns across stocks. But it's in a different way than we've seen before. So characteristics are going to help explain expected returns because they capture risk exposure to some factors that we're going to estimate now and that we haven't seen before. And it's not because they're anomalies. It's not because they're predictive of returns without absorbing, some sort of notion of exposure to a common risk. All right. Now, like I said, I'm going to be talking about lots and lots of potential characteristics because the literature on this now is huge. I'll say that some characteristics help explain expected returns. But when you do this test where you kind of jointly consider many potential characteristics simultaneously, a cool conclusion comes out of this. You don't need many characteristics. A small fraction of what's been proposed explains all you need to explain in the behavior of the cross-sectional returns. Most of the other stuff is redundant. It's showed up because of the way you've approached the testing problem before. But when you do kind of the right multivariate testing, you kind of see, all right, a lot of these things are redundant. We just need a few of them to capture all of the variation that shows up in returns. All right, so that's what I want you to take away. Here's the model. The model is extremely simple. Okay, so on the left-hand side, I'm going to have R here, which is an excess return on a cross-section of stocks. On the right-hand side, I have a conditional beta, and I have a set of factors, K factors. Now, the key structure of this model is that beta is going to be moving around, and the factors are latent. All right. Now, what I'm going to introduce that changes the problem from types of structures we've seen before is a set of conditioning characteristics that I'll call instruments. I'm going to denote these Z. All right, so I'm going to specify how these betas behave. The betas are latent. I'm going to use some observables to instrument for the time variation in the betas that we don't get to see. They don't have to perfectly absorb all of the variation in the betas, but they have to help us inform our estimates of the betas. They have to have some signal about what's going on in the betas. So what I'll have here, so think about the beta on some asset I. Asset I is also going to have, say, 50, 60, 200 characteristics. I'm going to take some linear combination of those characteristics that's going to be static across times and across firms. It's going to be a single model way of aggregating information and characteristics into a firm-level set of betas on the latent factors. All right, so let me go through what's actually happening when I write down this model and when I estimate this model. All right, so here I've written the model in a little bit more general way. I have my conditional betas here, which depend on some observable characteristics, and I've also introduced the possibility that I also have some alphas associated with those characteristics. So this is sort of the typical view of characteristics or anomalies in the literature. All right, so our motivation for writing this model is just that we want to admit the possibility that maybe what's going on with these characteristics is that they line up with average returns because they're showing up in the risk exposures. All right, and this is exactly the relationship to some of my discussing Kent's earlier work. All right, once I have a structure that looks like that and admits that possibility, the question that I'm going to really ask is, can I find some factors that are consistent with the characteristic expected return cross-sectional relationship that we've seen in the past? All right, so in the past, all of these characteristics have shown up because they predict returns. I want to know, do they predict returns because there's some latent factors and betas on those factors that are associated with the characteristics, right? They're just informative instruments for those exposures to these factors that we haven't seen. All right, now, it's possible that no such factors exist. It's possible that when I have characteristics at the firm level, they predict the returns of the stock, and there's no common factor that I could line up with those as a notion of an exposure. In that case, my model is going to dump the predictability from the characteristic into the alpha. All right, so it's sort of nesting these two ways of thinking about the world, the risk-based beta factor model view and kind of the anomaly, pure predictability with no risk point of view. And this is exactly where these nice test statistics are going to pop out of the model. There's going to be an intuitive intercept test, just like a Gibbons-Ross-Schenken test, that's going to ask, you know, am I seeing that characteristics forecast returns because they are representing, they're proxying for some exposures to these latent factors? Or is it because they're just good predictors of returns, but they don't actually come along with any risk? That is, they're so-called anomalies. All right. Now, there's one other feature of this model that I want to highlight, and it's showing up in this description of the beta. So I say here that this gamma beta matrix is key. What gamma beta does is it takes a potentially very large number of characteristics at the firm level. Think something like 100 characteristics, right? These are the types of numbers that we're used to looking at now in 2018 doing asset pricing. You have to think about a lot of these things. All right. So it asks, is there a way that I can condense all of the information in those characteristics into a small number of exposures? Really, what this matrix is going to do, it's going to build betas at the firm level by taking some linear combinations of this high dimension set of characteristics. It's going to say, what's the best linear combination of the characteristics for describing factor exposures? All right. Okay, so I'm not going to go through the details of estimation here. I just wanted to throw this up. This is the objective function for the problem. It's just a least squares estimator. I'm trying to minimize the squared return errors that come out of the model. This is exactly the PCA objective function. And this is exactly why we're going to end up with a pretty straightforward estimator. The difference is we have these time-varying betas showing up, and we have to handle that. So that's like the methodological contribution of the paper and the companion econometrics paper. But I'm not going to go into that detail here. Just wanted to show you how this kind of works in the background. Instead, what I want to do is give you a little bit more of an intuitive interpretation of the estimator. All right. So the exact estimator based on the objective function that I wrote down is on the previous slide. I'm not going to tell you about the exact estimator. I'm going to tell you about an approximation to the exact estimator, because this approximation has a nice interpretation. It's a managed portfolios view of factor pricing. All right. So here's what I'm going to do. I'm going to consider a large number of characteristics L. All right. In each time period, I'm going to run a cross-sectional regression of the returns at t plus 1 on an observed characteristic at time t. You've seen these types of regressions before. It's how you build managed portfolios on the basis of a characteristic. So every period, I'm going to run L cross-sectional regressions. I'm going to have a bunch of returns regressed on characteristic 1. Those returns regressed on characteristic 2, all the way up to characteristic L. Those cross-sectional slope coefficients, those are returns on a factor portfolio. Those are returns on a characteristic managed portfolio. Because L can be large, I'm essentially building a big matrix of characteristic managed portfolios. Think of dimension T as being like 800 or 1,000 months, dimension L as being like roughly 100 characteristics. So now I have all of this common variation that I can try and capture that exists in these managed portfolios. What IPCA does is essentially build this X matrix and then apply principal components to that, as opposed to applying principal components to the returns, to the stock level returns themselves. All right, so in other words, what IPCA is doing when it estimates factors, it's approximately the same as saying, what are the common sources of variation in all of the characteristic managed portfolios that we've looked at up till now? All right, in other words, the factors are themselves portfolios of a large dimension of managed portfolios. All right, now this gamma matrix is nice because it allows us to move from this portfolio level view of the world back to the stock level view of the world fluidly. It's a mapping that really makes the model equivalent whether you think about asset pricing at managed portfolio levels or at individual stock levels, right? This representation here is exactly what allows me to go from common factor exposures via PCA, and then I hit those with the characteristics at the firm level, and that gives me the betas to the factors at the firm level. All right, now, how do the asset pricing tests work here? I'm going to look at a couple. IPCA has some really cool asset pricing tests. We go through several of them in the paper. I'm going to talk about 2 of them in this talk. The first is just the typical 0 alpha restriction that we like to think about in asset pricing. All right, so the way that I'm going to evaluate the 0 alpha condition, the Gibbons-Ross-Shankin style test essentially, is to consider whether or not this gamma alpha matrix is 0 or non-zero. All right? So the null hypothesis is that all of the differences in average returns show up because of beta. All right. That means that I can think about whether or not this gamma alpha matrix deviates from 0 or not. All right, so this is, I want to come back to why I like using latent factor models. It avoids what I would call a common pitfall. It's not uncommon for you to do something like say, all right, I have a proposed characteristic and I'm going to build portfolios sorted on this characteristic. Then I'm going to go and regress those portfolios on the Fama-French factors. And then I find that those portfolios have alpha with respect to the Fama-French factors. All right. Are you finding alpha because there's alpha, or are you finding alpha because you used the wrong factors? Latent factors are less susceptible to this problem. Okay, so this is the test of whether or not there's alpha in these characteristics after you allow for some factor exposures, estimating the factors. Another interesting test that we can think about is which characteristics are important for the model. So that's like saying I'm going to look at some elements of this gamma beta matrix and ask, let's say, is the jth characteristic significantly contributing to my model's description of the cross-section of returns? So that amounts to a null hypothesis in which I zero out elements of gamma beta associated with a particular characteristic and compare that to the alternative in which I allow that characteristic to enter with non-zero effect. All right. So that's a quick overview of the theoretical structure, the model structure in the paper. Let me show you what it does in the empirics. All right, so the data that we're going to look at are monthly stock level returns and characteristics, typical sample. All right, so I'm going to look at 36 characteristics. These are characteristics that have been used in a recent paper by my colleague Michael Weber and some of his co-authors, but it's kind of all the usual suspects: size, value, momentum, accruals, yada, yada. All right. In the end, I'm going to have 73 characteristics because I'm going to do the following thing. I'm going to split characteristics into 2 pieces. One piece is just going to be their time series average. Okay, so I would call this C bar. All right? It's asking, like, do I actually need the time variation in the characteristics, or is it just the unconditional levels that are useful for describing risk exposures and the predictability of returns? All right? Or alternatively, do I need that time variation? That'll be captured by the deviations of the characteristics from their time series means. And on top of this, to sort of make sure that your betas don't look too weird, you always want to have a constant in your instrument vector. Now, I'm going to go through these results. Most of my results are going to be presented to you in the form of 3 statistics. All right, these are the 3 statistics that I want us to be thinking about. The first 2 are about assessments of how good a model is. If I have an asset pricing model, I want it to pull off 2 things. I want it to give a good description of risk, and I want it to give a good description of risk compensation. All right, so what do I mean by a good description of risk? I'll describe that by this object I'm going to call the total R squared. I'm going to fit the model, and I'm going to get these conditional betas and these factors. These represent the common variation in returns. So I'm going to ask, the total R squared is essentially asking how much of the total variation in returns is described by the common variation among returns. All right? And that's a contemporaneous notion of explanation. All right? It's contemporaneously explaining R with the realized factors. There's another notion of R squared that I want to think about that helps capture this risk compensation idea, and it's the predictive R squared. If my model is good at describing risk compensation, it should predict cross-sectionally the returns. In that sense, what I want to do is really understand if the conditional betas are lining up with the differences in average returns, and maybe the alphas if I'm allowing those in the model. All right. So this lambda is just the unconditional price of risk for the factor. We can talk more about that during Q&A if we want. All right, so these are the 2 ways that I'm going to assess my model. I'll show you a bunch of R squareds for a bunch of different model specifications. And then I'm also going to frequently show you a p-value. A p-value is a test for the 0 alpha asset pricing restriction. All right, it's just the standard no arbitrage restriction that we would be using if we were doing GRS. We just have a particular characteristic-based way of doing it in the IPCA setting. All right, so here are what some results look like. I'm going to choose a couple of different IPCA specifications with different numbers of factors. I'll look at 1 factor all the way up to 6 factors. And I'll look at 2 different specifications in terms of what's going on in alpha. In one specification, I'll fix alpha to 0. I'm only going to allow the model to explain returns via the factor exposures. And in the other specification, I'm going to loosen that up and see how much things improve when I allow for an intercept. All right, then here are your total and predictive R squareds. And here's the test statistic for whether or not the alpha is 0. All right, so let's start with the total R squared. First of all, these are monthly returns at the stock level. All right, so you should think roughly 20% R squared would be a really nice R squared to pull off. Okay, I'll show you some Fama-French results in a slide or 2 that are sort of consistent with that view. So the first reaction is, even with 1 factor, I'm actually describing a lot of the common variation in returns. As I increase the number of factors, I start to push about 20% explained variation. An important thing to think about is what's the difference in the explained variation when I allow for an intercept or don't allow for an intercept. And you see that in terms of total R squared, there's not much of a difference between these 2. All right, now next, how does this model do in terms of risk compensation? That's the predictive R squared part. Here, you see a big difference at first. If I only allow for a 1-factor model, what I see is that the restricted IPCA specification, the one that only allows you to explain return with betas, it actually doesn't do such a great job of predicting stock level returns. All right? And again, to give you a sense of what we should expect in magnitudes for R squareds, these are 1-month predictive regressions. So like if you predict the 1-month stock market using the price dividend ratio, you get about a 1% monthly R squared. So that should roughly benchmark these R squareds. All right. If I slacken the 0 alpha restriction and allow there to be some alpha associated with these characteristics, in a 1-factor model, my R squared goes up tremendously. It's like saying that 1 factor is just not enough to explain the differences in average returns, even if you allow yourself to estimate the factors. But here's the cool part. You start adding factors, you give your model a little bit more flexibility in the risk dimension, and you start to close that gap really quickly. This is a big enough gap that our statistic is going to reject that alpha is 0. It's going to find anomalies if you only have 1 factor in your model. But by the time you even get to just 2 factors, you say, I can't reject the null that these anomalies are 0, that there's no predictive power of characteristics for returns other than that comes through the betas themselves. All right, so the conclusion that this test statistic is telling us is that with 2 or more common factors, there are no anomalies. All right, now that, of course, begs a lot of questions. We know a lot about how kind of the world behaves. First of all, I've only showed you results among different IPCA specifications. The Fama French model, for example, it does generate small alphas on average. So how are we competing with that? And yeah, if I allow for 100 characteristics in my model, don't I start to have kind of a highly parameterized model? So let's do some comparisons with some other models. I'm going to focus on panel A and B here. So these are the results that I already showed you for IPCA. This is the shutting off the intercept component. This is everything coming through risk exposures. And this is what happens when you use observable factors. All right, it's going to be the Fama. OK, so k equals 1, that's CAP-M. K equals 3, Fama French 3. K equals 4, Fama French Carhart. K equals 5, Fama French 5. K equals 6, Fama French 5 plus momentum. OK, so it's like an expanded Carhart model. All right, so the first thing I want to look at is how do these things compare in terms of total R squared? They're actually really similar. Once you get to, say, a 3-factor model, actually the Fama French factors explain more of the total variation than IPCA. But I would argue that that shouldn't be surprising at all, because let's look at the parameterization of these things. If you think we have a highly parameterized model, because we have roughly 2,000 parameters, when you take stock level data and you run Fama French regressions onto 3 factors times each of your assets that you're looking at, 35,000, right? So yeah, they can explain the variation in returns contemporaneously, but you need roughly 20 times as many parameters as the IPCA model. All right. And even with that many more parameters, it's not competitive at all in terms of the predictive content. All right, so what this is telling us is that when you allow conditioning information to show up in your betas, you not only improve the explanation of the riskiness of your cross-section of assets, but you also improve the ability of those risk exposures to describe compensation for risk. All right, so I want to talk about 1 or 2 additional results. I'm running out of time. What I show you when I'm telling you that alphas are 0, that's equivalent to a statement that the factors that we estimate are multivariate mean variance efficient. That means that any assets that they price should show up with 0 alpha, and we should see that there'd be a high multivariate Sharpe ratio among the factors that we estimate. So what I do is I report here the average raw returns for a bunch of characteristic sorted portfolios, anomalies that people have looked at, and then the corresponding alpha after I run them through the model. So dark circles, these are significant alphas. Right? We should not be surprised that there are a lot of anomalies where regressing them on Fama French factors doesn't do anything. You have a 45-degree line. That's why they're called anomalies. But once you start regressing them onto IPCA factors, you essentially explain as many of these things as you would expect with the significant alphas showing up by chance alone. All right. Now, I can talk about the characteristics that show up as significant. They end up being log market equity size, a couple different variations of momentum, total assets, beta. All right. So what I want to conclude from this is that when you include many characteristics jointly, including a lot of sort of, the usual suspects, investment and profitability, most of these characteristics look irrelevant to the model once they're evaluated jointly against all other characteristics. All right, so we have some robustness. What I want you to take away from this paper is we have a new methodology that handles dynamic asset pricing models in a latent factor setting. It's easy and it's fast to implement. All right, and it comes with a lot of nice tests that go with it. The model performance is good. All right, it explains both the variation in returns, the risk, and the compensation, and it's adaptable. If you show up with the new characteristic, we can bring it into the model and adjust the risk factors that we have off of that. And I already went through these empirical facts. I'm over time, so I'll stop there. Thank you.